Hello, and welcome to my presentation on the hypoxic dead zone in the Gulf of Mexico. The objectives for this presentation is to define hypoxia, explain the history of hypoxia in the Gulf of Mexico, explain the effects of hypoxia, discuss the causes of hypoxia, and finally discuss what can and is being done to alleviate the size and effects of the hypoxic dead zone in the Gulf of Mexico. So what is hypoxia? Hypoxia is commonly defined as an area of water where the dissolved oxygen is less than or equal to 2 milligrams per liter. This is generally when biodiversity is greatly affected and numerous species aren't able to survive. This is why hypoxic zones are generally considered as dead zones. To the right is a satellite image of the hypoxic area around the Gulf of Mexico. As you can see, there appears to be a green film around the water, especially around the coastal land area. The green coloration is actually caused by algal blooms due to eutrophication, which we will discuss further in the presentation. The hypoxic or dead zone in the Gulf of Mexico has been well documented since the 1950s. It's important to know that dead zones do occur naturally. In fact, some geographic locations are predisposed to experiencing yearly hypoxia. However, as we will learn later in the presentation, human-driven factors cause these areas, especially in the Gulf of Mexico, to expand greatly. The Gulf of Mexico dead zone typically occurs from April to September. This is considered the largest and most severe hypoxic zone in the western Atlantic. The affected area has greatly increased over time. Between 1985 and 1992, the area was approximately 7,000 to 9,000 square kilometers, while in 1999, this had increased to 20,000 square kilometers. However, this has appeared to have stabilized over the last 20 years. This picture shows the 2017 Gulf of Mexico hypoxic zone. According to the EPA, the 2017 Gulf of Mexico hypoxic zone covered the largest area since it's been measured in the mid-1980s. As you can see, the area in red is what's considered hypoxic and is less than 2 milligrams per liter. Outside of the red zone are varying intensities of orange and yellow, which represent different levels of dissolved oxygen that still affect biodiversity, but aren't technically considered or measured as the overall area of the dead zone. Here we have a graph created by Nancy Robalis, Eugene Turner, the Louisiana University's Marine Consortium, and Louisiana State University that displays the varying sizes of the hypoxic area in the Gulf of Mexico from 1985 until 2019. As you can see, there is a pretty clear increase in the mid-1980s up until the late 1990s and early 2000s. However, after that, there is a fairly stabilized level between the early 2000s and up until the last 5-year period where we again see a slight increase happening. We also notice that there's quite a bit of fluctuation from year to year. For example, in 2000, that was the lowest recorded area of the hypoxic dead zone. Yet the following year and the year just prior had some of the largest areas ever recorded. So the main difference between these years, and as we see these fluctuations from different years, is due to a couple different factors. The first main factor is caused by how much precipitation the Mississippi River Basin receives. In years where there is heavy rain and lots of flooding, there's more nutrient runoff that gets into the Mississippi River, which makes its way down to the delta and mixes with the ocean water. This causes greater eutrophication and ultimately ends in a larger hypoxic area. Versus years where there are droughts and less precipitation, there's less nutrient runoff that we receive, and that causes these smaller areas of hypoxic dead zones. This makes it so we can actually predict year to year about how or what we would expect the hypoxic area to be depending on the rainfall in the spring. Another consideration is wind. Wind can play a pretty big factor as well, as if it's super windy in the ocean, there's more water that's being mixed, and it lessens the effects of eutrophication and lessens the land area of the hypoxic dead zone. So these two main factors are the drivers in what determines the yearly size of the hypoxic dead zone. But again, we can see a pretty clear increase from the mid-1980s until the 2000s, which makes us believe and suggest that it's due to increasing fertilizer use on agricultural land. This bottom dashed line is the task force goal of the size of the hypoxic dead zone of 5,000 square kilometers. Clearly, the long-term average is significantly greater. In fact, it's almost 3 times larger than the task force goal. Also, interestingly, in the last 5 years, we've also seen a slight increase in the 5-year average over the long-term average. And we can clearly see here in 2017 was the largest recorded area of the hypoxic dead zone in the Gulf of Mexico. So why are we concerned about hypoxic areas like in the Gulf of Mexico? What are the effects and what are the implications of having these dead zones? And more importantly, why should you care? First, let's discuss the environmental impacts that hypoxic zones have. So the main effect is the devastation that it can cause to the biodiversity of organisms within the affected region. More specifically, benthic organisms are the most affected. Benthic organisms are basically bottom-dwelling organisms, and the bottom of the ocean is where there's the least dissolved oxygen content, especially in these hypoxic zones. And so these are the most affected. Furthermore, these organisms, a lot of the species aren't simply able to move out of the zone like other organisms such as fish. And that makes them a lot more susceptible to the lessened dissolved oxygen content. And certain species, such as crustaceans, are even more sensitive to dissolved oxygen levels. For example, Cancer erotis in its larva stage has an LC50 at dissolved oxygen levels of 8.6 milligrams per liter. This is 4 times greater than what's considered a hypoxic or dead zone level, and the species still has an LC50, which is a lethal concentration where 50% of their species would perish. So obviously, certain species are far more affected than others, but it all has an effect on the balance of the ecosystem and affects basically the food chain in smaller species first, which can then have a cascading effect on the upper levels of the food chain. Because of the environmental impacts, there are also social impacts that are experienced. There's decreased fishing in the area, which can cause equity issues. For example, local fishermen may not be able to afford to go out further for fishing as compared to commercial enterprises. There can be a decreased use of recreation and decreased tourism as a result. Not to mention, this area can also experience toxic algal blooms as a result of the eutrophication. Although this doesn't always happen, it can happen when the conditions are right, which can create a further issue of not being able to use the water at all for any type of recreation. As we will see, these social and environmental impacts also have economic consequences. Not only is there social and environmental impacts due to dead zones, but there's also economic impacts as well. It's estimated that $82 million a year is lost in the seafood and tourism industry due to the hypoxic dead zone in the Gulf of Mexico. And this is a pretty devastating effect because Louisiana's seafood production is #2 in the United States, just after Alaska. And the reason being is because fishermen are forced to travel further to get outside of the dead zone to catch commercial fish, and there's even less commercial fish due to interruptions in the food chain. As explained before, lower species are more effective on the food chain due to hypoxia, but this has a cascading effect all the way up the food chain. So even fish that can simply swim out of the dead zone can still be impacted because they're not getting the same available items in their food chain as they would if there wasn't the dead zone. Now that we've discussed what hypoxia is, the history of hypoxia, and the environmental, social, and economic impacts that this dead zone has, it's important to understand what causes hypoxia in order to determine what possible solutions there are to address the situation. Fortunately, the cause of hypoxia is pretty well understood. The two main causes of hypoxia is from eutrophication and seasonal stratification. Eutrophication happens when there are excess nutrients. For the Gulf of Mexico, this happens when excess nutrients from the Mississippi and Atchafalaya River estuaries enter the ocean and mix with salt water. Seasonal stratification is basically when the top ocean layer doesn't mix with the deep bottom ocean layer. The top layer has a much higher dissolved oxygen content, while the bottom layer has a much lower dissolved oxygen content. And without the mixing of the two layers, the bottom layer generally becomes hypoxic and is then considered a dead zone. We'll discuss both of these more in depth next. All right, so what is eutrophication? Well, eutrophication is basically algal blooms in nutrient-rich waters. In the ocean, this is when phytoplankton thrive and reproduce. As the phytoplankton dies and sinks to the bottom of the water column, bacteria begin to break down the organic material and utilize oxygen, which then results in a reduction in total dissolved oxygen. As we can see from this chart provided by the EPA, we can see fresh river water coming into this top ocean layer. As it comes in, it provides a perfect habitat for phytoplankton to reproduce. And phytoplankton like to sit at the very top layer of the ocean because they actually photosynthesize, so they want the most amount of sunlight. Due to this, they actually do produce oxygen and can increase the total dissolved oxygen content in this top layer. But as we'll see, since they reproduce so rapidly, they also die rapidly and fall to the bottom of the ocean layer, which is where they are then decomposed by bacteria, and that bacteria utilizes the dissolved oxygen, decreasing the total dissolved oxygen in this bottom ocean layer. And again, a lot of species can simply move up into this top layer, which has more dissolved oxygen and can survive. But some species can't, like crustaceans and crabs. They simply cannot move fast enough to get out of that bottom layer and can perish. And then this creates a positive feedback loop because more and more organic material then is lining up the ocean floor and is being decomposed by bacteria, which is utilizing more oxygen and decreasing the oxygen content in this bottom layer. So then even some organisms that might be able to survive at certain dissolved oxygen content are no longer able to, and then the area becomes hypoxic or a dead zone. It's interesting to see that oxygen comes from the atmosphere, mixes with the ocean, and then again, it does come from this phytoplankton. And as we'll learn in the next slide, the main cause, not the main cause, but along with eutrophication, stratification is really just as important as to what causes these dead zones, because stratification causes this very distinct layer between the top ocean layer and the bottom ocean layer. Now that we've discussed eutrophication, it's important to discuss stratification. Stratification is just as important of a factor to creating hypoxic dead zones as eutrophication. And stratification basically just means that there are distinct layers. And in the ocean, we see this with distinct top and bottom layers, especially in this estuary zones where fresh river water enters and mixes with the ocean. So that fresh river water mixes in that top layer with the ocean, but there's a distinct line and distinct difference between that top layer and bottom layer. The top layer has a higher dissolved oxygen content, and the bottom layer will always have a lower dissolved oxygen content. Then when it's exacerbated through eutrophication, that bottom layer can become hypoxic, creating the dead zone. So there are two reasons for this separation between the layers. First, fresh water is less dense, so as it mixes with that top layer of ocean water, it creates a less dense area or less dense water content and remains on the top. And second, fresh water is warmer than deep ocean water. So the water that's coming from the Mississippi River is warmer and sits at the top. Now, stratification is seasonal, just like eutrophication. It doesn't happen all the time because in the winter months, when the fresh water is slightly cooler and there's higher wind, this can create the mixing between the two layers, which is then what brings back that dead zone into a normal dissolved oxygen content area. Again, though, the bottom layer is still always going to have a lower oxygen content than the top layer, but by mixing the two, you get a non-hypoxic zone, so there's still an oxygen content that can sustain more life. So we've now mentioned nutrients as the main cause of eutrophication, which is invariably the main cause of these hypoxic dead zones. And we've discussed phosphorus and nitrogen as kind of the two main nutrients that we're concerned about. So what is the one that we're the most concerned about for ocean water? Well, nitrogen is a limiting nutrient in most oceanic waters. This means that any added amount of nitrogen can greatly exacerbate the amount of phytoplankton that's grown, or algae that's grown on the top layer, because it's that limiting nutrient of why there isn't more that's growing. And conversely, and interestingly, phosphorus is a limiting nutrient in most freshwater systems. So when we're talking about ocean hypoxic dead zones and ocean eutrophication, we're generally more concerned about nitrogen, which the form of nitrogen, which is the way that plants uptake nitrogen, is actually nitrate. So it's pretty common that when we're referring to nitrogen in nutrient levels for eutrophication and other factors, it's referred to as nitrate instead of just the elemental form of nitrogen. Um, so that's the main thing that we're worried about. And sadly, the amount of nitrate in the Gulf of Mexico has tripled over the last 50 years, so which is a pretty clear defining measure for why we've seen such an increase in the hypoxic dead zone in that area. Now that we've discussed the causes of hypoxia and how eutrophication occurs and why nutrient sources are important and an important driving factor of eutrophication, it's important to understand where these nutrient sources come from. And the main culprit is, as we've alluded to earlier in the presentation, is from agricultural runoff. It's estimated that 52% of delivered nitrate and phosphorus loads into the water system is from corn and soybean cultivation alone. That's not including any other types of crops. And it's pretty clear that adding too much fertilizer causes a large amount of runoff into the local water systems, which can and usually do feed into the Mississippi River along that kind of grain belt of where a lot of our farmlands exist in the country. So how this happens is anytime it rains or anytime that these plants are irrigated, any excess fertilizer that's not uptaken by the plants can run off, mix with the water, which eventually feeds into river systems. It either, runs over the what we call surface water and will feed into a river, or it will slowly dissipate down into the groundwater, which then can eventually feed back into river systems as well. But besides agriculture, there's also urban runoff, which has an estimated 12% of delivered nitrate and phosphorus into water systems as well. So definitely not as significant of a factor, but definitely should still be considered and regulated in order to fix the problem of these hypoxic dead zones. And Again, a large portion of this is from fertilizer use in urban areas and suburban areas on your lawn and everything, where there's excess runoff. It goes into the stormwater system, which then feeds into the rivers and then travels all the way down and mixes with the ocean. And another culprit that hasn't been well studied or documented, but could certainly be a significant contributor, is turf grass and golf courses. Again, these apply large amounts of fertilizer throughout the year to keep the grass plush and the turf grass very green. And these are not as well studied again, and so we don't know quite the effects of these, but it's estimated that they do have an effect on the water systems and nutrient loads that we experience in the river and ocean waters. So definitely something that we expect further research to be conducted on, and expect to see again policy made that really attacks all three of these sources. So we're not just focusing on agriculture or just focusing on urban. We're kind of addressing all of them at once. So let's discuss some of the solutions that we can have to reduce the amount of nutrient runoff that we experience from agricultural land. First, we can install cover crops. These can reduce fertilizer needs by 91% after 4 years and can reduce the use of herbicides by 97%. And this has really, really great impacts on the reduction of fertilizer needed. However, it's not something that some farmers are too keen on trying or doing because it does take 4 years and it does reduce crop yields in those time. After the 4 years, the crop yields go back to normal, and there's some evidence that there's even increased crop yields. But for some farmers, that 4 year period can seem pretty daunting. So it's not as common as it could be, and probably won't be until there are significant subsidies um, to promote or to incentivize using cover crops. Another solution would be to have buffer strips along affected rivers, and this would address both agriculture and urban runoff. Buffer strips are basically planting native landscapes and native plants along rivers for a certain distance for the width on each side of a river, and it would act as basically a catch-all to catch and then filtrate a lot of the incoming nutrient loads and pesticide and other pollutant loads as well. And these are generally deep-rooted plants, so they also stabilize the soil along riverbanks, which then reduces erosion, which is a very big contributing factor to nutrient loads as well when you have large quantities of soil being added into the river system. So lastly, another solution would be to have rotating crop cycles. An example of this would be growing alfalfa between corn cycles to reduce nitrogen fertilizer needed. This is because alfalfa actually adds nitrate naturally into the soil, whereas corn needs to have nitrate added. It can't fixate its own nitrate. So by growing alfalfa in between corn cycles, you can actually have naturally added nitrate into the soil system. And really all of these solutions are good to help with topsoil, which is becoming a major problem in our agricultural system. We're losing a lot of the nutrients that are in our topsoil, which is basically causing us to have to increase our fertilizer loads in order to get the same yields, and kind of reverting back to some of these farming practices which have been used and aren't by any means new solutions or new ways to farm, but they have a significant impact on the efficiency of farming and soil health in general, as well as aiding in reducing nutrient runoff. Some additional ways that we can reduce the nutrient loads that end up in our river systems is to minimize irrigation after fertilizer has been applied and avoid applying fertilizer when soil is moist or when we expect rain to occur. This is probably the cheapest and easiest solution for farmers to employ, as it would have really no costs or effects on their yields. It's just something that they can do as a way to kind of plan when to apply fertilizer on their land. And it really would be in the best benefit for them as well because they would get the most out of the fertilizer that they applied, um, without having some of it run off right away, due to rain or irrigating their land. And we can also reduce the use or application of fertilizers to things like golf courses and turf grass and lawns. There really isn't a need or a reason to have plush, green, luscious grass year round or in the spring and summer months. And I think adopting more native landscape designs in these urban and suburban areas with more natural plants that have deeper root systems and are healthier for the soil in general would mitigate the need. Well, they would really eliminate the need for adding any additional fertilizer, which could decrease the total nutrient load that we receive in our river systems. And just as a closing note on the sources of nutrient loads and some of the solutions, it can be a common misconception, or it can be easy to point fingers at farmers or agriculture as a whole. But there really is no incentive for farmers to add more fertilizer than what's needed. It's not cost effective, and they are going to use the most efficient amount of fertilizer on the land, to optimize crop yields, but to not waste money on fertilizer because there is diminishing returns. It's not simply adding more fertilizer increases total crop yields. So there isn't necessarily an issue of farmers just not being cautious and just over fertilizing their land. It's more just learning more about land use techniques, and really ultimately boils down to the health of the soil and the land in general. Healthy land and healthy soil is what genuinely has the least amount of nutrient runoff, and creates a cycle in which the nutrients are actually recycled and reused with crop yields. Okay, so we've discussed how hypoxia occurs in some ways that we can prevent some of the causes of it, specifically eutrophication and nutrient runoff and nitrate in the water systems. So now let's discuss what impacts climate change may have on hypoxic dead zones, not just in the Gulf of Mexico, but throughout the entire world. And the main question is, could the dead zone get larger due to climate change? Well, there's a couple reasons to believe that it could. First, if there's warmer temperatures, that means that there would be warmer water. And if there's warmer water that's staying on that top layer, that would increase stratification, or that separation between that top ocean layer and the bottom ocean layer. And remember, the top ocean layer has a higher dissolved oxygen content than the bottom layer would. And stratification prevents the mixing between that top and bottom layer, which means that there would be less dissolved oxygen in that bottom layer, and it would continue to be less for longer periods of time. Another factor to consider is the unpredictability of rainfall and flooding that could exacerbate nutrient runoff. Now, if we applied some of the solutions we talked about previously, hopefully that would mitigate the amount of nutrient runoff that we would receive. But if we experience pretty unpredictable and large rainfalls and flooding events, especially along the Mississippi River Basin, that could still increase the nutrient runoff and cause a perfect storm of creating larger areas of hypoxic zones or dead zones. So it's not known for sure what the exact impacts of climate change is, and what that would have on the hypoxic dead zones in the Gulf of Mexico and throughout the world. But these are two factors and two considerations to make in what would likely exacerbate the problem. In conclusion, the Gulf of Mexico hypoxic dead zone is an environmental concern that requires our attention. Hypoxic conditions are created from seasonal stratification and eutrophication. Eutrophication is caused by excess nutrient runoff. For ocean water, nitrate is the limiting nutrient, which causes algal blooms. There are several simple solutions to reduce nutrient runoff. First, we can simply reduce fertilizer use. This can be done by installing cover crops, having crop cycles and rotating crops, and just applying fertilizer at the appropriate times. So applying it not before there's a rainfall event, not irrigating your crops after applying fertilizer, and making sure that the soil is dry when you're applying fertilizer. We can also increase native landscapes and buffer strips along rivers, which would help filter out any excess nutrient runoff before they enter into the river system. Lastly, we discussed the impacts that climate change could have and how that could exacerbate the problem and why it's important to address it now. I just want to conclude with saying that we will never get rid of the hypoxic dead zone in the Gulf of Mexico. It's a naturally occurring phenomenon, but what we want to do is to make sure that we have it to a sizable and manageable level, and we're not continually increasing the size and having greater impacts on the economy, on the environment, and socially. Thank you for viewing my presentation. If you have any questions, please feel free to send me an email with the email listed below. Thank you.